Having previously explored a variety of sentiment analysis tasks, in this project, I explore additional neural network architectures, showing how they compare and contrast and how useful and efficient they are in carrying out different kinds of prediction tasks. So to start off with, sentiment analysis is an area of research in NLP, which is natural language processing. And this is a branch of AI that focuses on how machines can process language in the same way that humans can. Through the manipulation of text data, AI systems have made remarkable achievements in terms of cognitive understanding and text interpretation. The scope of NLP is quite a large area of research, including areas such as semantic analysis, text classification, translation, question answering, text generation, and language modeling. Even if natural language processing may sound distant and unfamiliar to someone who hasn't worked with AI before, GPT-3, the engine powering ChatGPT, is basically entirely based on natural language models, such as transformers. The popularity and growing use of ChatGPT shows how having some basic knowledge of NLP can be useful to anyone. Among the many methods used in NLP tasks, sentiment analysis, which is also known as opinion mining, is a commonly used technique that involves determining the sentiment found in a given piece of text. A sentiment refers to the emotion, attitude, tone, or opinion that is expressed in a given text. Definitions of the words found in a sentence and the broader context in which they are applied can all be used to help determine the overall sentiment found in a text. Generally speaking, the goal is to understand whether the expressed sentiment is positive, negative, or neutral. And sentiments can be categorized further in terms of specific emotions. Sentiment analysis can be applied to various types of text data and is commonly used in industry to monitor customer opinions associated with certain brands or companies who want to monitor the sentiment expressed by users, the sentiment that they show in articles, social media posts, etc. But basically, the applications of sentiment analysis are pretty much unlimited in terms of text data and what you can analyze with it. So sentiment analysis is usually described as a task that categorizes a word or set of words, such as a paragraph or an entire text, into different categories. And usually these categories are divided into positive, negative, and neutral. This is probably the most common categorization, but the amount of potential categories used can be expanded, such as the data set used in this project, which categorizes text from Twitter data into 6 different emotional categories. Testing out different methods on a given analysis task is a crucial step in building a successful neural network. This is known as model selection, and it is a crucial step in development that cannot be overlooked. Model selection in this project involves evaluating and comparing different, in this case, neural network models and architecture to identify the one that is best suited towards a specific sentiment categorization task. Many different neural network models can be used to implement the task of sentiment analysis. And typically, many different model architectures are tested for their prediction accuracy before a final model is selected. Different variables are put into consideration for model architecture selection, such as dataset complexity and computational efficiency. The chosen model will make accurate predictions and will align with the intricacies of the dataset used and will provide a computationally efficient solution to the given problem. In the analysis, a data set of 18,000 tweet entries was used as input data for 4 different kinds of neural network models, where the data was split into a test, training, and validation set. In the data set, each tweet is categorized by sentiment and put into one of 6 emotional categories, which are anger, fear, joy, love, sadness, and surprise. These categories are also labeled numerically. And in terms of data cleaning, not much was really required. Only a few word organization tasks, such as tokenization, which is the process of breaking down text into individual units called tokens. And then stemming was also applied, which reduces words to their base form. For example, words such as search and searching would be reduced to their root search in the process of stemming. Count vectorize was also applied, which is a function that takes the count of each word in the data set. And then finally, the sentiment labels were converted to one-hot encoded labels before being fed into the neural networks. And then the analysis of the project involved using 4 different neural network methods to compute the prediction accuracy of the models. So basically, how accurately was the neural network able to predict the sentiment that is attached to a given tweet? So these networks were an artificial neural network, convolutional neural network, bidirectional LSTM, and a transformer network. And these 4 networks were trained at different volumes of input. So the first training involved 4 million parameters, then 500,000 and 100,000, in order to determine how these different neural networks operate at different input volumes and which network you'd want to select based on how much data you'd like to process. So first network, which is an ANN and is illustrated over here, has an input layer, hidden layer, and output layer consisting of individual nodes in the network. And basically, input data is fed in from left to right, and then this data is processed through various algorithms and functions to produce a specific output. And an ANN is among the most basic types of neural networks and can be applied to a wide range of tasks, including classification. So connections between the neurons or the nodes are associated with weights and biases, which are used to manipulate the raw input data. And then activation functions are used between layers to introduce non-linearity to the model. So the ANN used this network had an input layer of 18,000 units, which is, the network was too big to really illustrate efficiently. So this is just an example of how a neural network looks like. And the network had two hidden layers, the first with 50 nodes and the second with 15 nodes. The ReLU activation function is applied to the hidden layers, and softmax activation is applied to the output layer. And that's basically what was done with the ANN. Then the next network that was used in the comparison was a convolutional neural network. The architecture of a convolutional neural network is characterized by stacking layers in a sequential manner and is especially useful in the processing of image data. The network architecture consists of an input layer and convolutional layers that apply convolution operations to the input data using filters or kernels. And then following the convolution, the network is put through a linear activation function such as ReLU, and the polling layers are used to downsize the input data, often using methods such as max polling to extract the most relevant features before producing the output as a normalized layer. Then the third model that was used is a bidirectional long short-term memory recurrent neural network, which can be abbreviated as an LSTM. And basically, this network takes input sequences in both forward and backward directions. The architecture here consists of an input sequence and then a backward layer, which processes information in the opposite direction. And yeah, it's a bit more complex than the CNN or the ANN. And then finally, the last network used was a transformer. Transformers, they make up the basic architecture of models such as GPT-3 and BERT. And this involves an input embedding and an output embedding built on encoder-decoder framework. Then these four neural networks were all compared against each other at the different parameter numbers, 4 million, 500,000, 100,000. And then two types of charts were generated to compare how they were overall performing at this sentiment categorization task. So for example, here we have the performance of the networks at 4 million parameters. And these graphs portray the loss in accuracies for each one of the networks. Then the second kind of chart that was used was a confusion matrix to show if the networks categorize things correctly, how they were supposed to, in terms of the 6 emotional categories with the input data that was put in. And then the algorithm in the code showed the loss and the changes in accuracy through each training epoch. And basically, for all of these networks, as the epochs went on, the accuracy would increase and then flatten out at a certain level, and the loss would steadily decrease, kind of in logarithmic manner. At 4 million parameters, the LSTM was shown to have the highest accuracy. But one of the downsides of using the LSTM was that the computational speed was very slow at this volume compared to some of the other networks, which is probably explained by the increased complexity of model processing. in the LSTM. Then at 500,000 parameters, these charts looked more or less the same. And the LSTM was still shown to have the highest accuracy. In fact, the accuracy was a couple percent higher than for the other models. The other models pretty much have the same accuracy with this. So probably if you were using this amount of input parameters and time was not of much concern, then both at 4 million and 500,000 input parameters, the LSTM would have been the most efficient network. Then at 100,000 parameters, the accuracy decreased compared to the higher parameter models. So in the previous models, the accuracy were standing at around 87, 90%. Over here, we have 80%, 84. So I guess this is also a demonstration of how using a large number of input parameters can increase the accuracy of a network. And over here, the transformer was actually found to be the most accurate at prediction. And one of the interesting trends over here was that in the LSTM, the accuracy would increase up to 90%, and then it would slightly decrease. And same with some of the other networks, which indicates that if too many parameters used, this would cause overfitting, which is another problem that needs to be addressed and avoided in order to avoid problems with the network. And yeah, so so yeah, this shows how the process of model fitting is developed in a sentiment analysis task, and how the ideal model you'd want to use can vary between how many input parameters you have and what specific task you are trying to accomplish. So, for example, if computational efficiency is of importance, then you might have to sacrifice some model accuracy to choose a network that would be less accurate in terms of its prediction, but would compute faster. So yeah, this pretty much summarizes the investigation that was done. And thank you for watching.